was quiz or video. All right, so let's kind of do an overview here. So we started with a rate quantity perspective for integrals. So I'm not looking for mathematical expressions here, but just meanings of things. So the integral of what, in general, gave us what in the rate quantity perspective? The integral of what gave us what?
Rate of change.
Where is rate
of change gave us
So we integrated rate of change. No, we did not integrate rate of change. We integrated rate of change what?
with respect to
Times dx. That's part of the math. The times the dx. That's not just telling us we're doing it with respect to x. Times dx is part of the math. So all that together was what?
dx.
And what? Yeah, and what does that mean? mdx. A little change in y, right? A little change in small changes in the quantity. Dx is part of that. It's a product. It's multiplication. The rate times a little change in x gives you a small change in a quantity, and then the integral sign means sum them all up. And what do we get when we add up the small changes in a quantity? Total change in that quantity, right? Total change in that quantity. Okay, and then in the last couple of days we've been doing the area perspective, right? Area perspective. So how would you fill in the blanks here? Integral of what gave us what? Integral of what's that?
Areas under the curve.
Okay, yeah. What kind of areas under the curve? So you're talking about the left side?
Yeah.
So we integrated. What did we?
Small changes.
Yeah, was it? Yeah, it was like the areas of the little strips, right? So thin strips of area, right? Thin strips of area was what we integrated up. Thin strips of area to get total area of a region, right? Total area of a region. For a couple of days on that. And so now we're going to do the volume. We're going to start volume perspective today. And we should now, it's the same thing over again, right? So what will we be integrating to get what? What will we be integrating to get what? It won't be cubes. We'll do different things, okay? So it'll be, thin elements, all right? So there's going to be different elements that we'll have, but they'll be thin. And they'll be like thin elements of volume. And we're going to get total volume of a solid. So that's what we're going to start today. But you see the commonality with integration. There's this commonality with integration. You integrate a typical little bit of something. And then you sum all those little bits up to get the whole, or the total change, right? So there's this like common theme with integral. Doesn't make sense. Okay, so let's do this. We want to find the volume of a solid formed by rotating R. R is the name of a region around the x-axis. R is the region formed by y equals 0, y equals x squared, and x equals 8. What is y equals 0? What is that? Y-axis? X-axis. Okay, make sure. This is a common mistake students make. They look at y equals 0 and they make that the y-axis. No, this is the x-axis. It's all the points where y equals 0, and that's the x-axis. Okay? So first of all, could we sketch that region? So practice that. So what region is that talking about? Y equals 0, y equals x squared, and x equals 8. Could you sketch that region first of all? Do it. Think you got it? Here's what it should look like. Not that. This. Okay? So did you get something like that? So that's not to scale, but that's the general idea of it. Get rid of this. No. There we go. That's what I want. Okay, and so what did it say? We're going to take that. That's the region R. So here's our XY plane. That's the region R. We're going to take that region R, and we're going to rotate it around the x-axis. And every point in space that that area hits will be a point in the solid that we want. So we're going to rotate that around, and everywhere in space that region passes through is part of the solid. Can you imagine what the solid will look like when we do that? So yeah, around the x-axis, right? Around the x-axis. Okay, so can you imagine, so every place in space that region is touching becomes part of the volume. So can you imagine what that will look like? Kind of cone-ish, right?
Really long base or really wide base.
Okay, so it's like a Hershey's Kiss. Do you see that? So everywhere in space where that thing rotates around, wherever that hits, becomes part of the solid. So it's just like this, or maybe like a bullhorn, but it's solid, right? It's solid all through and through, like a Hershey's Kiss. Okay. So how are we going to do that? Oh no, we're not even close to doing an integral yet, right? So no, we're going to start with a strip. Yeah, so we're going to start with a strip. So you start with a strip. Let's make it a little bigger out here. So you see the strip. So we're going to start by taking the strip and rotating the strip the same way that we're rotating the region. So if we rotate that strip around, that will be our volume element. Okay, what we get when we rotate a typical strip of the region around is what will be our typical volume element. So what will we get when we rotate that strip around? So maybe. Does it show up better now? There we go. Okay. All right. So I heard a cylinder. Will it be a cylinder? Really flat cylinder, and then someone said a pancake. That's exactly what it is. It's going to be like a pancake. Imagine that solid, okay? So imagine that solid. That's what we'll get. And so then what will happen? So we'll have all these pancakes, and then we'll get all the pancakes and we'll add them all up. Okay? So each strip, when wrapped around, when rotated the same way that the region is rotated, gives a pancake, and then that'll be our volume element. And we're gonna sum up all those pancakes as they get very, very, very thin. Just like as our strips got really thin, we got the total area. As the pancakes really, really thin, we'll get the total volume. Okay? And that's back to this. So that's what we'll get. Okay, so let's do it. So what do we need then? We need PowerPoint. Yeah, so we know what that solid is now. You sketch the region. It looks something like this. Okay, when we rotate that region, we got something like that. Okay, so then we said, all right, take a typical strip and do the same rotation on that typical strip that we do on that region. And what does that give us? A pancake, right? Yes. Okay, and so what we're going to do, we're going to do the volume of a typical pancake. So what is that? So we know that shape is what?
Cylinder.
Which has the volume of?
1 r squared or pi r squared.
Area of a circle times the height. Okay, so again, we're imagining, so there's our strips. So here's that pancake relative to that strip.
H is dx.
Okay, so h, the height of the cylinder is this little dimension right here, right? The height is this little dimension right here. What is that? Delta x, right? That's the same as our little width of our strip there, or the base of our strip. Okay, and so then all we have left then is the radius of the pancake, and we ask the question: is it an x coordinate, a y coordinate, a change in x, or a change in y? That radius of that pancake, is it x, y, change in x, or change in y? So that's our radius. So we come back here. So the radius is basically the height of that strip, right? The radius is going to be the height of that strip. X, y, change in x, change in y. It's just y, right? It's just y. It's just a y coordinate. Do you see it? It's just the distance from the x-axis up to the curve. That's a y coordinate. So the radius equals y. Yeah.
So it's only y instead of change of y because you're always comparing it to a fixed axis. Like, because you're always comparing it to the x-axis.
What is the y coordinate of a point? So if it's y because what is the y coordinate? See, I got to put a point right here. How would you describe the x coordinate and the y coordinate of that point? What does the y coordinate mean? Yeah.
Deviation from the x-axis.
Yeah, so it's how far if you're plotting that point, you go over this far, and then you go y, you go up this far, right? That's y. Y is how far you are from the x-axis, basically. So because we're rotating about the x-axis, that becomes the radius of this thing. Now, if you want to call it a change in y, it's fine, and you'd be doing y minus 0, you see, and then you just get y. It's okay, but it's just simpler to recognize it as just a y coordinate, and then you're done. You don't have any subtraction to do. Okay, but then we have delta x, so we have to rewrite that in terms of x, and so we do pi times, what is y? Yeah, so y is defined by this curve, and y equals x squared, so it's going to be x squared squared delta x, and we're done with our typical pancake. The volume of the typical pancake is pi x squared squared delta x. So we're ready for the volume of the kiss. Equals. So now we're going to talk about all the volume elements, right? So the very lowest x element is this little teeny pancake right here at the point. That is x equals 0. And then the very last pancake is the furthest to the right, 8. It's easy given to us, right? So we're imagining all those pancakes stacked up vertically, starting at x equals 0, ending at x equals 8. And then we're going to sum up those volumes. So look, dx is part of the volume, right? It's that height of that cylinder. We need it's part of the math. This is multiplication, right? So that the whole thing, that whole integrand with the dx is the volume of an element, in this case, a pancake. Yeah, please. What's that? Oh, that delta x became dx when we got really small, right? So this was just like one kind of non-small pancake. And when we add them all up, we want to be really super thin, and so that's that. Yeah, okay. Any other questions? Does it make sense? Okay, so let's try. So super easy integral, right? Super easy. Okay, so now we want to rotate it around x equals 8. Instead of rotating it around the x-axis, we want to rotate it around x equals 8. So same. Okay, so this time I'm gonna show it a little more realistic here. So if it was 8, this is more realistic, but still not quite to scale. But now what are we going to do? We're going to take that same region R, which we had before, right? And now I'm going to rotate it around x equals 8. So we're going to rotate it around this axis here. Can you imagine what you'll get? It's going to be really, really tall, and what's it going to be?
Like a Christmas tree.
Yeah. Yeah, so it's actually the same kind of shape as before, but now this is going to be really, really tall to the point. Whereas the other one would have been really, really wide, and this is 64, right? So this is the part 864. So that original thing that we did was really actually what 100. Its diameter at the bottom was 128, and it was only 8 tall. This one is going to have what a diameter at the bottom of 16, and it's going to be 64 tall. Okay, so it's the same kind of Hershey's Kiss or Spire kind of shape, but much different proportions. Much different proportions. Okay, so
the same area.
Okay, well they have the same volume.
That's what I meant.
Yeah. Good. So will they have the same volume?
Kind of seems like they will, but
Let's test it out. We'll set it up, and other one's easy to do, so we'll test it. Okay. Who says yes?
now we have
Who says no? Who doesn't care? Okay. All right. So you should care. So now to get pancakes, what's our typical strip going to be like when we rotate this thing to still get pancakes? Yeah, so you see that we're going to need, do red this time? I'm going to start with a red strip this way, and then I'm rotating around. So when I rotate around, it'll come around. When you rotated it 180, oh, that's really bad. Much better. Okay, so then this is kind of the shape it will have. It will look like this. Okay, which is half or something, but solid, right? It's solid. And so then our typical element will be another pancake like this. And so we can draw that up here. Okay, and this is our radius. And what is the height of the pancake? She said delta y. Agree with that? Delta y, right? And so we're going to have our volume of our typical pancake is a little volume. And it's still a cylinder, so it's still going to be pi r squared h. This time h is delta y, and then we come to the radius again, and we ask, is it an x-coordinate, a y-coordinate, a change in x, or a change in y? That radius. So that radius is actually what? From here to here. So we're going to go back to the original region in the typical strip, and that's our radius right there. Is that this dimension of that typical strip? So how would we define what that radius is? R equals, so final value of x minus initial. So 8 minus x. 8 minus the x-coordinate of that curve is what the radius is. Do you see it? Rightmost of the radius to leftmost of the radius. So it would have been helpful if I drew it on this side. And if I drew it over here, that's more helpful. Right, so right there, that's at x equals 8. And this is defined by what? The curve. What about the curve? That's the x-coordinate of the curve. So therefore, final x minus initial x is 8 minus x. That's the radius. But we got to get that. Now we're doing delta y. So we need x in terms of y. Square root of y, right? So now it's that curve y equals x squared, but we need x in terms of y, which is the square root of y, and only the positive because we're here in the first quadrant. So we got it. Okay, questions on the volume of the typical? So we use discs or pancakes. Okay, disc or pancakes. So that those terms mean the same thing. A solid disc or a pancake, we got the volume of it. John?
Can you do the same one with respect to x from 0 to 8 and then multiply the integral by 2? Is that equivalent?
What do you want to do now?
So instead of doing it with respect to y,
Mm-hmm.
would you be able to do it with respect to x, but only from 0 to 8?
If we do it with respect to x, we start with a strip and we rotate about 8, we don't get a pancake. We get something else. You wouldn't have to multiply by 2.
Okay.
But we'll do that. We're doing it. That's the next topic. So we're sticking just to whatever it takes. We're going to set up these strips so that we get the disc, right? The disc or the pancake. If we were to do that, what kind of thing would we get? This is a preview of things to come here. So if you did this and rotate, so we're still going to rotate at about x equals 8. What do you get when you do that?
Just a bunch
A hollow ring.
Yeah, so what we're going to get is, it's going to be hollow, right? And it's going to go around like that. It's going to be hollow. So if we had done a vertical strip and done the same rotation around 8, we get what's this called a cylindrical shell. It's like a sleeve. It's like a sleeve. Like you put your hand right through it. And it's really thin that way. For another day, okay? Stay tuned. Okay, so then we wanted to find out, are these the same volume or not? So we've got our volume of our kiss number 2 is from, are we going to integrate from what to what? Okay, so we need to get all these pancakes. The first one is at, now these are y's now. First one's at y equals 0. Last one's at? The very one is like a point, right? It comes to a point. It's the very smallest one, 64. So pi times 8 minus. Okay, so let's see. Same volume or different volume? Okay, Jason, it's up to you. What is it? Different or the same?
Does not compute.
No, they're different. They're different. First one was 0 to 8, x to the 4th dx, is that right? Oh, pi. There's a pi in there, right? Second one was this one that we just did. Is that the result we got for the first? Is that the integral we set up for the first one?
Yes.
This one is 0 to 64. Of, I'm just going to use x. We used y, but I'll just switch it back to x in this. Pi times 8 minus square root of x dx. Same or different?
Very different.
Very different. Did I do something wrong? Oh, I didn't square it. Didn't square it. Okay, wait a second. Here's the moment of truth.
Almost the same.
Oh no, they're off by a factor of 10, right? The first one was 10 times bigger. That first one's like 10 times bigger than this tall, skinny one, right? So that one that was squattier, that big squatty fat kiss was 10 times as big as the tall, skinny spire kiss. Yeah, so the way that you rotate it matters, right? It's not the way that you rotate a region is gonna affect the resulting volume. So just because it's the original same region, the rotation matters, right? The rotation matters in terms of what volume you get. Questions on these two examples? Okay, you need to try one yourself. Let's see here. All right, so there's something different about this, but see how you do. So it's the same starting region again, but now I'm going to rotate about the line y equals 70. Y equals 70. So let's just figure out the geometry. So see if you can if you can come up with the volume yourself, like what solid it is, what the solid is like. Same region revolved around y equals 70. So we're just trying to visualize this and get our best sketch that we can right now, okay? Just trying to visualize it and get the best sketch that you can. Straight line here. Okay, this is harder, okay? This is what you get. So when you rotate that thing around y equals 70, that's actually not, it's not one of the edges of our original region. So because it's away from the region, you rotate it and you get this hole, right? So you get this hole in the middle. So this is like a cylindrical bowl with a hole in the bottom. It's like a toilet or a really weird roll of toilet paper or something like this. But it's like we could turn this on its side and try to fill it up, but then everything would run out the bottom because there's a hole at the bottom. But so that where's the solid? The solid is all this part, right? The solid is all in this part. That's what's actually solid. The volume that we're going to measure is actually that part there. And all the rest is open space. Okay? So, if we want flat disc type things or washer type things, are we going to do vertical strips in here or horizontal strips? So if we do horizontal strips, we'll have those shells that I talked about, right? That I showed you before. So we're going to do what? We're going to do vertical strips. And so now you got to imagine, take that vertical strip and now rotate that around 70. You do the same rotation on your strip that you do on the whole region. Whatever you did to the region to get the whole solid, you're going to do the same thing to the strip to get the elements, right? So to get the typical element. And when you do that, do we get a pancake? And if not, what do we get?
Pancakes was removed from a larger pancake.
Right. So we get like a pancake with a pancake cut out of it, right? It's like what's called, we call a washer. So let me draw that. So when you rotate that thing, you're going to get, yes, you're going to get a pancake like on the outside, but then it's going to have a big hole in it. Okay, so look like this. Let me try again so it might help you to draw it better. That's doable, but if I draw it better, then it might help you to draw it. So let's try again. Okay, that's better. Okay, so now. And then you draw over here, you draw, there we go. That's better. So this is the element we get. And so we call this no longer a pancake, we call this a washer. And you see that that's what you get when you rotate that strip around the line y equals 70. Do you see that's what you're going to get? Can you imagine that? So now what's the volume of a washer? What's the volume of a washer?
Cylinder of the outside ring, or minus the cylinder of the inside ring.
Is that what you're going to say? So yeah, so it's like one big cylinder minus a smaller cylinder. Okay, so it's going to be volume outer minus volume inner. And each of those themselves are a pancake, right? So the outer is the whole thing as a pancake, and then the inner is like just the size of the whole as a pancake. So they're each going to be pi r squared h. So we're going to have pi r outer squared h minus pi r inner squared h. Does it make sense? So what is our height of both of them? Delta x or y? Delta x. Okay, so that'll be our height for both. Let's start with the outer radius first. So the outer radius, okay, use the original region and rotating line. Okay, so the outer radius is what? From here to there. That's the radius outer. Okay, so is it an x coordinate, a y coordinate, a change in x, or a change in y? Our outer. It's just simply a y coordinate, right? And we know what that y coordinate is for every single one. What is that y coordinate? Doesn't matter which washer you're looking at, it's always going to be 70. Do you see that? In this particular case, it's always going to be 70. So we can just do 70 squared. And that's the y coordinate of that rotating line. So yes, it is a y coordinate, but we know what it is. It's 70. Equals 70. Okay, and so now what about the inner radius? So the inner radius is from there to there, right? So that's our inner radius right there. X, Y, change in X or change in Y? That's a change in Y. So it's going to be Y2 minus Y1. Y2 is 70. Y1 is the Y coordinate on the curve. The Y coordinate on the curve. So we're doing a change in Y, so 70 minus just Y squared. Do you see it?
Wait, why is it just 70 minus y? No, that's right.
Because it's just the Y, this inner radius is that Y coordinate minus the Y coordinate on the curve. So that's just Y, 70 minus Y.
But that's all squared.
That's all squared. That whole thing, 70 minus Y, is the radius squared. But now we have delta x, so we're going to change everything that's Y into x. We have pi times 70 squared. Delta x minus
Next to 70 minus y. There's a pi.
a pi. You're saying pi. I kept saying, thought you said I. Okay, thanks. So we need pi there, that's right. 70 minus y is squared of just x squared, squared delta x, and that's our volume of our typical element. So here, this is a case in point where you don't want to try to write the integral from the beginning. So a lot of these problems that we've done with the areas, you might have been able to just go right to the integral and write it down. But so all this doing the typical element thing, typical strip, typical pancake, this is where it pays off, practicing that, because when you get something complicated like that, you don't want to jump right to the integral. You want to think this through and really work on that typical element in isolation. Now we're ready. Now the integral is easy, because once we do that, we just kind of copy it down again. So the volume of the thing is, so now we got which washers do we want? Starting at the left at x equals 0. That's going to be the one with the biggest hole and the least volume, right? The biggest hole and the least volume, and then all the way to the one with the smallest hole and the greatest volume is at x equals 8 pi times 70 squared minus pi times 70 minus x squared all dx. Again, this is multiplication. In terms of that volume, dx is part of that volume, right? dx is the height of our washer, part of the math. Please. Yeah.
This probably doesn't matter, but can you split that up into two integrals too? Or?
If you want, yeah. So just whenever you're subtracting two terms, it's the same as the difference of the integrals, yeah. But that just ends up being more writing and not less work. You just end up writing more. Other questions? Okay, cool. So now you're really going to do one by yourself, because we've exhausted kind of all the possibilities here. Can I erase? Last chance. Good one.
So this region would actually extend further out like this, right?
Okay, so question.
Yeah, can you factor out pi out of these?
Yeah. Yeah, when you're subtracting, they both have pi. Okay, so for time's sake, we better talk here. So you've got these. So I outlined the region in black here. I've outlined the region in black. X-axis, x plus y equals 6, x equals y squared. When you rotate that about x equals 9, you get that reflected over here. Same thing at 180 degrees. The whole thing then rotated looks like this. He said it perfectly. It's a dog bowl with a hole in it at the bottom. So original region was this right here, right? That was our original region, rotated around x equals 9. Okay, so then our strips are parallel to the x-axis. When you rotate that around, you get this washer here, the horizontal washer. And so then the inner radius, x, y, change in x or change in y? Change in x. X final minus x initial. X final is 9 minus the x coordinate of the line. And that's going to be our from x plus y equals 6. Outer radius. X, y, change in x or change in y? The outer radius, is that an x, a y, or a change in x or a change in y? It's another change in x. Outer radius is? Or outer, sorry, not outer radius. A final x value is 9. Initial x is the x again, but for a different curve, right? That's also x, but this time for x equals y squared. So I think you can take it from there. We're going to have, so your volume, again, of your volume of your washer is going to be volume outer minus volume inner. Volume outer will be based on that radius. Volume inner will be based on that radius. And our height of both of them is delta y. So I'll keep writing this out. If you want to check the end of the video, I'll keep writing, or you can stay, and I'll write out what this is.
Jason, I have a quick question. So on the first one, when the webwork things, you can solve x, but then it asks you to also do it with y. So, but then you get like the plus or minus the square root, and then you have to do that for in two intervals or one on the plus side. So, would you write that like as an expression would just be square root minus the negative or its own volume, so just like it's 2 times the square root.
That's a y coordinate. Whatever that y coordinate is. I think it's 2, 4, 2, y equals 2.
It's like rationing. You gotta get them when you can get them right.
They're so good.
Okay, any questions?
Wait, is it
1/3. Which one? I don't think there's a 1/3 anywhere.
You're making x or x plus y or 6 minus x equal to x.
I need the x equals 6 minus y. Okay? This is going to be 9 minus 6 minus y.
Then I meant for the upper bound.
Oh, the upper bound?
Yeah.
I think it's y equals 2, right? Because 2, 4 is the point. That point is 2, 4.
Oh,
No, 4, what I mean, 4, 2. 4, 2. 4, 2. That's point 4, 2. When x is 4, y is 2. And x is 4, y is 2.